In this video, I'm going to be talking about the three different types of bonds. We have covalent bonds, and these are the strong bonds that result from sharing of electrons, and they can be either polar or nonpolar. We have hydrogen bonds that are relatively weak, and we'll talk a little bit more about hydrogen bonds in a minute. And then we also have ionic bonds, and this is the attraction of complete ions, positive ion attracted to a negative ion. We'll talk about that more in a second as well. The covalent bonds are very, very strong, and they actually can only be broken by a chemical reaction, whereas hydrogen bonds and ionic bonds are both relatively weak, and these can both dissolve in water. Now, our understanding of bonding really starts with our understanding of the periodic table and the different requirements of the elements within the periodic table to reach their octet rule, as well as the idea of electronegativity. So if you need a little bit more information on that, refer to one of our other videos from Chapter 2 on electronegativity. However, in a brief reminder, we know that the top row here with hydrogen and helium, they have 2 electrons in the outer shell. Pretty much all these other rows, at least the ones that we're interested in, they have 8 electrons in the outer shell, and that's the rule of 8. So they're trying to fill their outer shell, and they can do this by either gaining electrons, potentially through bonding, or stealing electrons, or by losing electrons. So let's take carbon, for example, and you can see that carbon is right here on the periodic table. And so here is its shells, and so it has 2 electrons in the first shell. And the outer shell, which can hold up to 8, has 4. Thus, carbon's valence is 4 because it needs 4 more electrons to fill the outer shell. And here we add a hydrogen, and hydrogen has 1 electron in its outer shell, but remember, its outer shell only needs 2, so its valence is 1. It needs 1 extra electron to fill that outer shell. It's halfway there, so to speak. So one of the ways that hydrogen can fill its outer shell is by sharing an electron with carbon. And this actually helps carbon as well, because carbon has now just gained 1 electron towards having its outer shell filled. And this is a covalent bond. This bond here, whereby we have electrons being shared by 2 different atoms, that's what we mean by sharing of electrons. This is a very strong bond, and this is a covalent bond. Now, because carbon has a valence of 4, it needs to make 4 different covalent bonds in order to gain the 4 extra electrons it needs to have its outer shell of 8 filled. And so that's where we get this 1 carbon bound to 4 different hydrogens. And all of these are the shared pair of electrons, the covalent bond. So this carbon has 4 covalent bonds, each one with a hydrogen. Now, because these atoms, carbon and hydrogen, have similar electronegativities, these would be what we call nonpolar bonds. In other words, those electrons are shared equally, neither is winning the tug of war. And therefore there is no polarity. Neither carbon nor hydrogen is keeping the electrons a little bit further, and therefore neither has a dipole. Both have retained their neutral charge. On the other hand, if we look at water, now we have oxygen bound to 2 different hydrogens, and that's because, remember, oxygen's valence is 8, so here are the shared pairs of electrons. That's the covalent bond between oxygen and hydrogen, and here's another one. These elements, oxygen and hydrogen, however, have different electronegativities. Oxygen has a higher electronegativity, and thus the electrons spend more time around oxygen, giving it a negative dipole, and therefore the electrons spend a little less time around the hydrogens, giving them a positive dipole, and that creates a polar covalent bond. Now, hydrogen bonds require 2 polar bonds coming near each other. Now, for example, if we have a water, oxygen with its 2 hydrogens, these lines here, they indicate our covalent bonds, the shared pair of electrons. We know, because this is polar, that we have one end that has a positive dipole, and we have the other end that has a negative dipole. So when waters start to line up next to each other, here we have 1 water molecule, and here we would have another water molecule. Again, remember, the solid lines are our covalent strong bonds with the shared pairs of electrons. But now our positive dipole is going to line up and become attracted to the negative dipole of the oxygen on this other water. That is a hydrogen bond. So those hydrogen bonds are formed when 2 different molecules have their opposite dipoles that come together and attract. And we can have this with pretty much anything that has polarity, so that you have a positive dipole, and if it comes in contact or near another molecule that has a negative dipole, the opposite dipoles attract. Those are hydrogen bonds. Now, not only does this work for water molecules interacting together, but this will work for any polar bond. So we have a carbonyl here with the carbon double bonded to oxygen, and then we might have a amine group. And so we know that this carbon double bonded oxygen is polar with a negative dipole here. This nitrogen and hydrogen is polar, and hydrogen has the positive dipole. So if this was to interact with water, this is going to create a hydrogen bond with the hydrogen on a water molecule. They're going to line up that way, because the oxygen with its negative dipole would actually repel, but the hydrogen with its positive dipole attracts there. And the opposite is true over here with this hydrogen. That hydrogen is going to be attracted to the oxygen of a water molecule, because again, the opposite dipoles attract, and there's your hydrogen bond in the dotted line. Now, in a sense, the extreme version of this is an ionic bond. And this is where we're not just talking about dipoles, but actual full charge ions. And so if you think about it, especially over here in our metals, for all of these elements, sodium for example, it is much easier for sodium to fill its outer shell by losing its one extra electron than it would be to gain 7 others. So it actually can quite easily lose that electron and become a positive ion. Over here, chlorine, for example, it has a really high electronegativity because it just needs to gain 1 electron. And so it's more than happy to steal that electron from sodium. This is not a shared electron. This is not a covalent bond. This is a stolen electron. But this, again, leaves our sodium with a positive cation charge and chlorine as an anion with a negative charge, and those opposite charges attract, and they are going to bond together. And if you do this over and over again, you have sodium chloride, and a salt crystal will form, where sodium and chloride alternate. Now we know that salt crystals can dissolve in water, and that's because this attraction can be broken apart by water, because they can create hydrogen bonds with the water molecule. So for example, our negatively charged chlorine ion here, they're going to be attracted to all the hydrogens of a water molecule. On the other hand, the positive charge of the sodium are going to be attracted to the oxygens of water with their negative dipoles. And in doing so, water can basically split these two ions apart into the sodium ion and chlorine ion. That's why ionic bonds break in water. So in summary, covalent bonds are when 2 atoms are sharing an electron, and this is a very strong bond, and those bonds can be polar or nonpolar, depending on electronegativities involved. Hydrogen bonds are when opposite dipoles created by polar covalent bonds attract. So these are 2 separate molecules attracted together by opposite dipoles. That's hydrogen bonds. And then ionic bonds are when one cation is attracted to an anion. And this isn't sharing electrons, but basically one atom has stolen the electron from the other. The resulting charges, opposite charges, then attract.